Well, hello again, students everywhere. And from that little introductory video, you can know that I'm going to be talking once again about Newton's laws of motion. And I should add, by the way, that car accident was completely staged. The children didn't get burnt to death in the flaming car, but it does show you where Newton's laws can save our lives. So let's go on and look a little bit about Newton's second law of motion. Just to recap, the acceleration of an object is directly proportional to the net force and inversely proportional to the mass of the object. And it's in the same direction as the net force. Right, let's analyze those words. Directly proportional to. It means if one goes up, the other goes up. If the acceleration is proportional to the force, if the force increases, the acceleration increases. For a bigger acceleration, you need a bigger force. They go up together. That's what direct proportion means. They go up together. Inversely proportional to the mass of the object. Inversely proportional is like a seesaw. If one quantity goes up, the other goes down. If one quantity goes up, the other goes down. So if the mass increases, the acceleration will decrease. If the mass increases, the acceleration decreases. If the acceleration is going to be bigger for a given force, the mass will have to be smaller. So acceleration and mass are like a seesaw. Acceleration and force are like that. That is direct proportion. That is inverse proportion. So the acceleration is proportional to the force over the mass, which means, by the laws of proportionality, which you will have learned, that the acceleration equals a constant, a number, a fixed number, multiplied by force over mass. Now, the clever thing is, if we use newtons, kilograms, meters, and seconds, the value of this number k is just 1, which makes it dead simple. So if k equals 1, the acceleration equals the force over the mass. Or, rearranging, bringing the mass up, force equals mass times acceleration. The standard thing we all know about Newton's second law. Force equals mass times acceleration, but it's important that you get the units right. The force has to be in newtons. The mass has to be in kilograms. And the acceleration has to be in meters per second per second. Now, some people get confused by this unit of acceleration. Some people say meters per second per second. Well, what's per second per second? It's not meters per second, it's meters per second. And if you think about it, it's a change in velocity. Velocity is in meters per second. So it's a change of velocity in meters per second every second. So meters per second change per second. Meters per second per second. So after the first meters per second, pause before you say the next per second. Meters per second per second. So that's acceleration. Remember, when doing any calculation with Newton's second law, always check your units. And if you're given a time in milliseconds, or a mass in grams, or an acceleration in kilometers per hour, you have to change it to newtons, kilograms, and seconds. Now, there is an example in your textbook, the same textbook that I showed you in the last lesson, there's an experiment to show Newton's second law, or to demonstrate Newton's second law. Some people talk about an experiment to prove Newton's second law. This experiment will not prove Newton's second law. In fact, it's very difficult to do an experiment which proves anything, because in every experiment there is experimental error. So in order to verify Newton's second law, you may have to carry out 1,000 experiments. And even then, you can't be certain that the 1,001st experiment doesn't show Newton's law to be wrong. So be very careful. This experiment demonstrates how you could verify Newton's second law if you did it 1,000 times. And there's a trolley and a string and a pulley and a weight hanging down here. And the weight pulls the string down, which makes the string pull along, which makes the trolley accelerate forwards. And you do this for a whole lot of different weights hanging here, and you can even change the mass of the trolley here, and you make a table of all your results, and this will show approximately that Newton's second law seems to work. But don't forget, in all experiments there is experimental error. So no single experiment proves anything. And so don't say this is an experiment to prove Newton's law. Now, one confusion people have sometimes when carrying out this is in your textbook, so look at all the details in your textbook. One confusion people have, the force which comes from the force of gravity pulling down on this weight, the force isn't just accelerating that trolley, it is also accelerating the mass, the hanging mass as well. So the total mass being accelerated by gravitational force is the mass of the trolley plus the mass of the hanging weight. And you have to remember that. And one question asked in the textbook is, why do you have to take that mass into account? And the answer is because the force of gravity is also accelerating that mass downwards too. So have a look at that experiment and be able to explain how to try to prove or verify Newton's second law. But remember, in every experiment there is always experimental error. Now, we can summarize Newton's second law of motion using what I call the triangle of remembrance, because if you put F equals ma in a triangle like this, it's very helpful. Force equals mass times acceleration. Okay, if in a problem you want to know what the acceleration is, cover acceleration with your finger and you're left with force over mass. So to find the acceleration is the force divided by the mass. If you want to know what the mass is force divided by acceleration. So you simply find out what the force is, what the acceleration is, and the mass that's being moved will be found in kilograms by putting the force over the acceleration. That triangle is really useful to help you remember. All you have to remember is force equals mass times acceleration. Write it down like that, and you cover the one you want to find, and the answer is what's left. Mass is force over acceleration. Acceleration is force over mass. And this triangle of remembrance is to help you remember. It's not physics. It's just a little way of writing them down to help you remember. And it works for things like V equals IR, Ohm's law, V equals IR, or any other situation where you have a little formula with three quantities in it. So remember the triangle of remembrance. Force equals mass times acceleration. And remember again, you must check your units, because if the units are not correct, you will not get the right answer. Well now, do you remember we began by saying that Newton's second law in your textbook says that the force is equal to the rate of change of momentum. And you'll remember that momentum is mass times velocity, and it's the property of a moving object which makes it want to keep on moving. Newton's first law. If it's moving, it wants to keep on moving, and you need a force to make it change. Momentum is mass multiplied by velocity. The bigger the mass, the more difficult it is to get it moving or stop it. The bigger the velocity, the more difficult it is to stop it. So mass times velocity is important, and that is momentum. But rate of change of momentum is, how is the momentum changing every second? The rate of change of momentum. And we have a nice quantity here called impulse. Now, impulse, you know the word impulsive. Somebody is a very impulsive person. They do something without thinking. They act without thinking. They throw the ball and it breaks the window because they didn't notice the window there. They act without thinking. They're impulsive. So impulse is a sudden something. And in physics, the word impulse talks about a force and how long you're exerting that force. If I'm going to push a car, how many seconds am I pushing the car for? The force multiplied by the time that the force is working. The force acts, the bigger the effect on movement. The longer you push, the faster the car. The bigger the force, the more change in the movement of the object. So impulse is defined in physics mathematically. Impulse is the force multiplied by the time of action of the force. How long are you exerting the force for? And it equals the change in momentum. You notice not the rate of change, because now we've got time up here, so we don't need time in the change of momentum. Force times time is equal to the change in momentum. So force multiplied by time equals change in momentum, and that tells us that how long you push with the force determines how much change in movement you're going to produce. And remember the word impulse, because impulse is the change in momentum, and I can have the same change in momentum by, if I can find a board writer, I can have the same change in momentum by exerting a small force for a long time, or a big force for a short time. Big force, short time, or little force, long time. The two multiplied by that together, force times time. So, for example, a force of 15 newtons for 3 seconds will produce a change in momentum of 3 times 15 is 45. But if I think of a force of 5 newtons times 9 seconds, that equals 45 as well. So, a force of 15 newtons working for 3 seconds produces a change in momentum of 45 kilogram meters a second. The same change in momentum can be produced, instead of 15, a force of 5, but a time of 9. So, a big force for a short time can have the same effect as a little force for a long time. Now, if I draw a graph, I don't know whether the camera can see this, but let's do force times time. A big force for a short time and a small force for a long time. Now, if you think about it, force times time, that length by that length, equals the area of the graph. Similarly here, force times time, or I should say force times time, equals the area of the graph. And the area of these two graphs is the same. Equal areas. Big force, short time, small force, long time. So each of these two will produce the same change in momentum. So as a general principle, and it's in your textbook again, if we draw a force time graph, the area under the force time graph is equal to the change in momentum. Now, this has big effects. Remember, if I want to stop a car, I can have a big force for a short time or a small force for a long time. And if you're not careful, if you try to stop Sue suddenly, you will find that you have a big force for a very short time, and the big force is not very pleasant for the human body. So this collision here, the force to stop the car, was a big force which acted for a very short time. Whereas if the car had put on the brake pedal, it could be a small force for a much longer time. Now, what that really tells us is this. If you're looking at the force that acts on you when you crash your motor car, which of course you will never do because you will be careful drivers, but if a car does hit a brick wall, it doesn't matter how fast the car was going. What matters is how quickly it stops. Big force for a short time, much smaller force if you stop over a long time. And this is the principle behind the whole issue of car safety. If you think about it, it doesn't matter how fast you're going. The Drucker Airbus, when it lands at Paro Airport, hits the runway at about 200 miles an hour. Now, if you can imagine going in your car and hitting a brick wall at 200 miles an hour and stopping suddenly, you wouldn't live. But the Airbus lands and then the brakes are applied and it takes the whole length of the runway, perhaps 1.5 minutes for it to stop, instead of 1/100th of a second if you hit a brick wall. So the Airbus plane travelling at 200 miles an hour takes a long time to stop. Small force, long time. And remember, it's not how fast you're going that hurts. It's how quickly you stop. And if you stop too quickly, this is what happens to your very precious and expensive motor car. And one way we help save ourselves from being badly injured in a car accident is by wearing a seat belt. So now I just want to say a few words about a seat belt. Let's put those papers away, and instead of paper, let's come now to my computer. Impulse, force times time, equals change in momentum. If you want to stop something, you can have a big force for a short time or a little force for a long time. Now, this is really important to understand if you want to make sure about safety. We've mentioned car safety, and I'll go on to seat belts in a moment, but even if you're sending something by Amazon, something you've ordered from India, you don't want it broken when it gets to Bhutan, and so you arrange packaging. Here's the sort of stuff you might package something in. And you'll notice if a force is applied to this, it moves in like that. Now, this means that instead of stopping suddenly in 1/100th of a second, if something bangs into it, it stops over perhaps 1/10th of a second, which is 10 times longer than 1/100th of a second. So the force will be 10 times less. So this sort of packaging material is an example of Newton's second law of motion in action. You are reducing the force by having a lower, smaller deceleration, and you are having a smaller force for a longer time. And so this is really important. You use this if you do judo. You land on a mat like this. If you landed on a hard concrete floor, you would stop very suddenly. So you'd have a very big force for a short time. With this, you get a very long time to stop and a much smaller force. The same thing applies if I'm knocking a nail into a piece of wood with a hammer. Now, if I have the hammer, think of the mass of the hammer, it's massive, and I'm going like that, so it's moving. Mass times velocity is momentum. I have to take away all that momentum when it hits, and there's a piece of wood, there's a nail, and you can hear that when the hammer hits the nail, bing, bing, it stops very suddenly. The hammer stops suddenly. If the nail were actually on a piece of wood, which was on this foam, and I tried knocking the nail in, it's not so effective. I need this wood to be on a solid surface so that the hammer stops suddenly, not like that. Now, what I might do is, without thinking, while I'm just demonstrating like that, I might remove the foam and go boomf like that, in which case I would break my knee, which would be unfortunate. However, I talked of deliveries by Amazon. Well, there is one particular type of packaging which is very, very important, and that is the great steel boxes that they put nuclear waste in. And nuclear waste has to be carried from a nuclear power station to the place where it is going to be left. And so it has to go on a train or on the road. And if it is in a steel box which is not sufficiently strong, then if there was a road accident, the box might hit the ground and break open. If it was on a train accident, there might be a train crash and the box splits open and the radioactive waste escapes all over the place. So, when they first started to build nuclear power stations and to have to move the nuclear waste, they designed very special, very strong steel boxes to put them in, and they tested them. One way they tested one of the boxes in England was to put it on a railway track and make a train bang into the box. And here's a very old video of that test that was done in England.
Now to driver.
There's the train, and it's got 8 miles to speed up.
Every inch of the journey was followed by cameras mounted on a helicopter, and the train's speed was checked by engineers using radar guns. Eventually, it reached 100 miles an hour.
100 miles an hour for the train, and it's going to bang into one of these steel boxes.
Watched from a safe distance by some 1,500 invited guests, it ploughed headlong into the derailed flask and wagon. "32 different cameras captured the scene from many different angles. There was even a camera on the front of the engine. But we at it, it was a tremendous test of the strength of the fuel flask.
And indeed, the steel case carrying the fuel, there was no nuclear fuel in that test. It actually had a ton of water in it. And this test showed that this steel flask was capable of withstanding some very, very bad accidents. But I hope you noticed that when the train hit the flask, it didn't just stop like the hammer did, hitting the nail, pop. The front of the train went crumpled like that. So actually the train stopped over 2 or 3 seconds. It didn't just go it went like that. It stopped over 2 or 3 seconds, which reduced the force. And this is where we come to car safety and the car seat belt, which I'll show you another little video.
More than 1,000 children 12 and under die in car crashes every year, and more than 100,000 are injured. But parents can reduce the risk to their kids if they put them in an appropriate car safety seat that's correctly installed in their vehicle. When a vehicle is moving at 30 miles per hour, so is everything inside it. If the vehicle crashes, unrestrained objects keep moving at their original speed until they strike the vehicle interior. This is why infant and child car seats are so important. They hold child passengers in place as the vehicle's front end does its job of crumpling and absorbing energy. This test demonstrates something parents don't even want to think about: an unprotected infant smashing into the instrument panel. Some parents think it's okay to ride with a child on their lap, but it's not. Crashes happen so fast and are so violent that you can't protect a child this way. Frontal airbags can be especially dangerous. In a crash, an airbag can hit a child or car seat with tremendous force. Even older children shouldn't sit in the front seat. The temptation to play with the radio can put them in harm's way. Children are always safer in the back seat. The basic types of car seats are rear-facing infant seats, forward-facing child seats, convertible seats that can be used either rear or forward-facing, and booster seats for children who've outgrown their forward-facing seat but aren't big enough for adult seatbelts.